Okay, I wanted to work an example problem using an op-amp circuit, an active element, and also one that has a capacitor or an inductor in here so that you can see the Laplace domain approach for writing a model that would represent this circuit. Okay, so we're going to take the Laplace domain approach. So what that involves would be to instead of using the time domain, we're going to take the Laplace transform of VI and we would get capital VI. And we'll take the Laplace transform of the output, that would be capital V out. And resistors stay the same in the Laplace domain. And we talked about a capacitor turns into, when you take the Laplace transform, you get 1 over CS of a capacitor element. All right, so this is our circuit in the Laplace domain. And what I want you to be able to do with op-amp circuits essentially is to recognize patterns, because that's typically how you're going to do this. If you wanted to make a summer circuit, for example, you'd look that up. If you wanted to make an integrator circuit, you would look that up. So different forms of circuits are what I'm after. And we had talked about this special case. Okay, if we look at a quick circuit, this is an inverting amplifier. We had derived this output, RF, RN. V out is minus RF over RN, VN. Okay, so we are using this idea. We know about this circuit, we've already analyzed it. So what I'm wondering is, can you match up what corresponds to RI and RF? Okay, so let's use two different colors. Okay, so the RF is fairly easy because it's the same element in the circuit. So that's the RF, all right? But the RI would be this impedance combination. All that plays the role of RI. Okay, so I look at that and I have R1 in parallel with 1 over CS. All right, so I could write down Z1 is equal to R1 in parallel with the 1 over CS, and a parallel combination of impedances is 1 over R1. If I do 1 over CS, I just get CS, and then I take the inverse. Okay, so that's the first impedance. And so I could get Z input, the whole yellow thing all put together, because R2 is in series with Z1. Okay, so that would be, because it's in series, it'd be R2 plus Z1. Okay, so essentially, now we've got it. V out over V in is equal to minus RF divided by Z in. Okay, so that's the transfer function. All right, so what I'm going to do next is I'm going to turn to Matlab to do all the grungy calculations, and we'll see how this matches the solution that you can download from Professor Miller's homework assignment. So this is, the same homework practice that I put up in Module 5, and you'll see this is an easier way to analyze this circuit. Okay, so let me go to Matlab. Okay, here is the Matlab solution for the problem that we've been looking at. So, as usual, I define the symbolic variables. I calculate that first parallel impedance. Okay, so that was 1 over R1 plus 1 over CS. So you flip that back and the CS comes back to the top. And then you take the reciprocal of all that. So that gives you the parallel equivalent of R1 and C in the Laplace domain. And then you add in R2 to get the input impedance for this inverting op-amp structure. So remember what we're doing, we're matching a pattern where we see that you have this feedback resistor that's going, feeding back from the output to the negative input of the op-amp, and then you have an input impedance on the front end that's these three circuit elements. Okay, so from there it's just the formula. The gain formula for an op amp is minus RF over Zn, but now Zn is a function of S. Okay, so we plug that in, and let me change the format here to put it in line. Okay, so we have the Z1 impedance, the Z input impedance, when we add that in, and we take minus RF over Zn, that's the transfer function. We simplify that with the simplify command. Okay, and then you collect everything on as powers of S, and you get this transfer function. Okay, and so what I wanted to do is confirm that this gives you the same answer that you see in the solutions that I provided for the practice homework. The solution was a different tact. It used completely a time domain approach to get to the final answer, and I think hopefully you'll find this Laplace domain approach is much quicker and more straightforward to apply. Okay, so but I wanted to compare these answers, so let's plug in some values and make sure they work out to be the same. I also wanted to talk to you about some tricks to make Matlab simplify things where you can compare two different symbolic expressions. Okay, so when I do this, these are defining some variable quantities, and then to make that evaluate, there's an evaluate command. So h is equal to eval h, and so that substitutes these variables that I've defined into the symbolic expression. Okay, so when you get that, you get this answer, and what I want to do is manipulate this to where the S on the bottom is by itself. Okay, I'm sorry, by itself. It has a coefficient of 1. Right now it has a coefficient of 150. So I want to factor out that 150, and that way I can compare two different symbolic expressions more easily. So what I do here is I extract the numerator and the denominator of h with the numden command, okay? And then the v equal coefficients, right? It's pulling out the coefficients of the denominator, okay? And so when I do that, it looks like it did some simplification. So I guess you can divide out the 50 here, and you get the 3 and the 160. That's neither here nor there. The point is that I need to normalize by the second term. All right, so here's V2. If I take the denominator and I divide by V2, and then do the same thing on the numerator, I'm essentially multiplying and dividing by the same number, so I don't change the expression. And so the bottom line is, when I substitute that in, and I put this VPA in comma 4 here so that it doesn't give me just a ton of precision. All right, so let me show you what happens if you don't do that. Okay, so you get all this precision that it's trying to carry with this symbolic toolbox. Okay, so we're just trying to compare our answers, so let's truncate that to 3 or 4 places. That should be good enough. And we see our result. Okay? All right, so what I've done in the next step, I take the answer from the answer key for the work that I gave you that has the time domain solution. It has a slightly different form of the expression, and I'm trying to convince you that these are equivalent. Okay, so I just typed that in straight from the solutions. Okay, so scrolling down a little bit, if I can. It's not letting me scroll. Oh, darn. All right, move the whole window. Okay, it won't let me scroll because it's on one screen. All right, so here we go. I typed that in, and we've already defined C and R1 and R2 and RF. All right, so it evaluates that answer, okay? And so what I want to do is simplify this to where the S is by itself. So I do that same kind of numden, separating out the numerator and the denominator, looking at this coefficient here and dividing by the highest, the coefficient that's on the S term, and piecing it back together, and I see that I get exactly the same answer. Okay, so two different approaches that I've illustrated here. One is in the solutions write-up that is provided on Canvas. The second one is the subject of this video. So hopefully, I know this takes a while to explain, but ultimately, it didn't take me very long to do this problem once I took it to the Laplace domain. So the capacitor became 1 over S. I made Vn equal to 1 essentially, and actually I used the formula for recognizing the form of an inverting op-amp structure. Okay, so I had the input impedance in the denominator, the feedback impedance minus RF in the numerator, and so the formula is H equals minus RF over Zn, and that's what gave me the work. Okay, so I let Matlab do most of the heavy lifting here, and we were able to come up with a model for this circuit.